It's now time to move on to the next contribution by Professor Yang Gao, FIET, and Fellow of the Royal Aeronautical Society. So Professor Gao is Professor of Space Autonomous Systems at the University of Surrey and heads the multi-award winning Space Technology for Autonomous and Robotic Systems Laboratory. She specializes in robotic, sensing, perception, visual GNC, and biomimetic mechanisms for industrial applications in extreme environments. Professor Gao brings over 20 years of research experience in developing robotics and autonomous systems, having been the PI of international and national team projects funded by UK Research Innovation, Royal Academy of Engineering, European Commission, ESA, UK Space Agency, and more. She's also actively involved in design and development of real-world space missions, including ESA ExoMars, Proba3, and more. Besides her own research activities, Professor Gao provides a range of professional services to the wider space and robotics community, such as being the editor-in-chief of Wiles Journal of Field Robotics, and also she's mentor of the United Nations Space for Women program. So, Professor Gao, it's an honor to have you today with us and learn about AI robotics for sustainable space exploration and exploitation. The floor is yours.
Thank you so much, Gabriel, for the very kind introduction. And hello, everyone. Thanks for the opportunity to speak to you today and share some of my views and experience on AI-empowered, AI-enabled robotics for space. Hope people can see the screen okay.
Yeah, the screen is fine. Yeah, great. We can also see the slides
moving forward. That's great. So just before I start going through some of the technologies we've been developing for the past 15 odd years, just to highlight our motivation working in AI robotics techniques, we are really trying to achieve two goals in the long term. One is to improve the autonomy, the level of autonomy for future spacecraft, and secondly, to help diversify the locomotion capabilities for future space system. So this explains why our key focus has been looking at the 3D perception, the real-time visual navigation, reconfigurable autonomy, biomimetics or bio-inspired mechanisms. And they are generic solutions that can facilitate spacecraft, space robotic systems for both orbital scenario as well as planetary surface scenario. So starting with the orbital scenario, it has been widely acknowledged that there are many on-orbit applications that would require advanced artificial intelligence, robotics capabilities in the time frame of 2025, 2035. So this is quite an ambitious goal, and the time is clicking, as we can tell. And the range of mission applications are also very widely spread out. We're looking at debris removal challenges, on-orbit assembly deployment, spacecraft servicing, formation flying, constellation, reconfigurable satellite systems. But from the technological point of view, we know that this could present to us quite different challenges, meaning we have to deal with non-corporate targets as well as corporate targets. And we will be looking at robotics or robotic system being deployed from either pseudo-fixed platforms such as a space station or free flyers, such as the medium size or even small size satellite systems. The first example of technology development I'd like to share today is to do with formation flying, and this is a mission coordinated by ESA, called Prof 3, where the goal is to demonstrate precision formation flying of two spacecraft to help study solar corona. And the work we are collaborating with industry is really looking at one of the payload system, which is a critical payload system, laser-based, fine lateral and longitudinal system looking at relative altitude determination between the two spacecraft. And the aim is to achieve a high accuracy of 300 micron at the longest distance of 250 meters between the two spacecraft. And the key challenge here technically is to try to address the lateral measurement system, because the beam motion can have a significant impact on accuracy of the measurement. And here we adopted some machine learning techniques, particularly during the phase of the testing, the validation, and calibration stage to achieve the scientific objective. Due to time limitation today, I cannot go through the technical details. That's why I included all the reference and in the published domain so people can pick it up. The second example is to do with the visual navigation in orbit, looking at a target spacecraft for example, servicing and assembly in orbit. So this is what we regard as corporate target, that you have some reliable information about the target object that you need to navigate relatively. But as we know, there are a lot of challenges around the limited computational capability on board even the modern spacecraft. And we have challenges in terms of, for example, the environment is very challenging from the visual perspective, and there are also uncertainties, sensor noise that you want your algorithm to be capable of addressing. So our solution here is we limit ourselves by just using monocular vision for post estimation so that we can meet the low computation fast speed requirement from the spacecraft hardware. But we're also adopting the CNN solution, the convolutional neural network based deep learning, so that we can meet high accuracy and adaptability requirement coming from the mission performance point of view. In order to validate our algorithm, which of course are quite novel, we have also developed photorealistic orbital visual simulators so that we can produce quite realistic data set to validate, so that what this film is showing. And also you can see some pictures that coming from our simulator that can produce varying data set for different mission scenarios. But similarly, we are demonstrating the technique also using Earth-based orbital testbed, as is playing on the film here. And you can see that in real time, the algorithm can still recover when there is a lose of sight on orbital target, and still recover and perform that docking quite realistically. I'm just fast forward in the film because of the time limitation. So you can see that even with the change of field of view there with a target object, the docking can still be successfully performed. And moving on, we talked about the object could be non-cooperative. So for instance, we will be looking at, manipulation grasping with such object, for example, the active debris removal scenario. Similarly, the techniques we're developing here can work with limited hardware processing power on board the spacecraft, because we use sparse point cloud sensing and visual guided GNC. And it can also be quite noise and uncertainty resilient. So just to demonstrate how this works, everything is tested and demonstrated both in the digital simulator as well as the physical test bed. So the two films that are playing kind of echo and show the very consistent results. So here the target object is, we're using the spanned upstream motor as example. So another interesting thing I want to highlight is we also introduced verification and validation techniques. I think that's the point being mentioned by previous speakers, being important, because when you're introducing artificial or machine learning related techniques, one of the concerns is about whether it's verifiable in real time. So this is another novelty we introduced from scientific point of view. So moving on, planetary surface scenario, if we look at over the horizon, there are a lot of planned missions in the sort of sample return type of interest. There are, for example, the Chinese Chang'e 5 and their follow on, the Chang'e 6 going to the moon and collecting sample planetary from the far side of the moon. And of course, there's a joint venture between ESA and NASA on Mars sample return. And here the robotics are playing a role in terms of fetching rovers and sambaler from both surface and subsurface. And of course, moving beyond 2030s, we might be looking at manufacturing assembly, in-situ resource utilization. There's ESA's Moon Village initiative. There's a recent announcement from China and Russia's joint venture on international lunar research stations, etc. Of course, there's commercial interest there. So there, robotically, we're looking at heterogeneous robotic element, building those infrastructures. We're looking at also human-robot ecosystem, potentially around, for example, the south pole of the moon. So here are a few examples of the techniques we've been developing to facilitate those visions. One example is looking at autonomous visual GNC for high accuracy robotic arm placement for sample acquisition from the planetary surface. And here we also look at visual saliency-based approach that address more robust feature tracking for homogeneous scene, which are things, for example, you look at rocky terrains, you look at granular particle-based regulus surface conditions, and these are very stressful for classical vision processing techniques. So we have to introduce artificial intelligence to give us the extra capabilities to perform good trade-offs between computational load and detection accuracy and precision. So here, the film that is playing is showing you how we're changing the feature detection techniques at different range between the target object and the robotic arm and effector, and particularly when you're moving to a closer up field of view of the rock where everything looks very similar. That's where you start to switch to more saliency-driven techniques in order to provide you that reliable visual guided GNC result. Moving to another example, which kind of move to a different scale of image processing, if you like. And this here we're looking at quite a large image data processing compared to the previous example. And this is where we get data from the Chang'e-3 mission provided by the scientific team from China through a collaboration funded by Royal Academy of Engineering. Here, our contribution was to perform a very deep analytics on the extremely high resolution surface data from the Chang'e-3 rover. Where we combine that image processing with our knowledge of chiromechanics that allowed us to make a prediction or estimation of the soil property in terms of the strength or soil stiffness. And we applied the same methodology on data coming from the Apollo 15 and Luna 17, so that we can compare their landing site conditions under the same sort of kind of measurement. And this is a very interesting comparison that has been later used for their later mission, for example, the Chang'e 4 and 5. Similarly, there are also interest to look at this kind of data analytics for future Mars mission. The AISTAR2021 rover mission is one of the possible example. Here we're collaborating with the ExoMars PanCan lead based in UCL and looking at this kind of automatic, autonomous, intelligent data pipeline processing system that allows us to create a very useful GIS system combining the processing of the imageries as well as understanding of the operation of the rover. And that system can eventually be used by both the science team as well as the engineering team for operating the rover. I want to quickly go through another two important, I think, work in terms of the mobility capability for future robotic system. And this is to do with the mechanism designs rather than just the software design. This is very often being overlooked by perhaps the community in general, because when people talk about mobility mechanism, they often don't immediately connect that with artificial intelligence. But I would argue that there's a very important lag of using AI or AI empowered for the mechanism, which I call AI embodiment research. So here's an example of a bioinspired method for enhancing the surface mobility of future rovers. Apologies, so go back. So here, for example, I'm playing two videos that is showcasing a work we're doing here by introducing an active suspension design, which is inspired by biological behaviors such as crawling and climbing. So on the left-hand side, the two films are showing the crawling behaviors for surface and entrapment traverse using very small number of actuators, which actually in this case only 2 motors. And on the right-hand side is on the same platform, same design, demonstrating that the climbing behavior for rocky and step traverse. Again, I'm showing you the digital simulator as well as a physical system demonstration, which shows consistent results. And also we introduced the deep reinforcement learning to enable the GNC or the control in particular for this type of designs and particularly automatic tuning of the parameters that can cope with quite a smart mechanism. This example here is to go beneath the surface because, as being said earlier, the subsurface sampling and drilling is equally important to achieve a lot of visions we have in the space community. And here is also a Bioinspired method for drilling and sampling under microgravity environment. So on the top-hand side here, I'm playing a film about the mechanism itself that allow very low, lightweight and low power operations. And you can see I'm playing on the left-hand side. On the top here is the simulation. This is a real actual simulation showing the drill interaction with the granular particle in the regulars. Well, on the left-hand side is actual physical test. And on the bottom here, I'm showing the same mechanism performing the sampling task. So again, there's a digital simulation as well as the actual, test system. And so just maybe a last view of my slides. What I want to say is looking forward. What are the gaps currently in the technical knowledge, and which I personally, this is my personal view, so very much just very open for discussions and criticisms. I personally believe the key word here moving forward for AI robotics is sustainability. So how to design future robotic system embedded with artificial intelligence to allow sustainable presence of spacecraft space systems. In the intermediate term, my personal view is that we have still a number of things outstanding or being an open issue. And this is very much to do with how we come up with reliable solutions that cope with the hardware constraints and the very high demand for reliability, self-verification of space systems. So very largely driven by that. And in the longer term, this needs to be in place in order to achieve long-lived, robust mobility and autonomy for future generation of spacecraft. One of the example I very much want to stress and really call for a joint effort from the community is to move from the weak AI to strong AI. And I'm giving an example here of some of the preliminary work we did looking at reconfigurable autonomy that would be domain independent, generic, reusable software architecture that really allow us to integrate the capability in terms of learning, planning. Of course, our existing solution is ontology-based modeling solution, but this is not the only solution. The film that's playing here is really showing some of the preliminary results of this concept that allows reconfigurability at hardware level, at software level, that can cope with changing environment or uncertainties in the environment. So that concludes my talk. I hope that's tolerable by colleagues, but very happy to take questions if there's time, but if not, happy to be contacted offline. Then I'm very happy to carry on discussions.
Very inspiring talk, Professor Gao. I think you shed light on so many topics. It was super fascinating. I have a lot of questions for you. Let's see, I will just ask a few. I just remind all participants, if they want to ask questions, they can do so through the Q&A tab at the bottom right of WebEx. So one of the things I was quite interested in was actually, so you mentioned autonomous docking for a cooperative target, and I was wondering if you have any idea of how your methods compare to SpaceX's solution. I saw that you put sorry, Dragon as one of the 3D model you used to check the autonomous docking. And as you may well know, also SpaceX Dragon is using autonomous docking to dock to the ISS. So I was wondering whether you have some sort of comparison there.
Sure. No, that's a very good question. In fact, in the simulator we developed, the futuristic simulator Orbital. One of the purpose of developing that in-house is because we found out that it's very difficult to compare existing algorithms under the same umbrella. So we developed that in order to create data sets so we can compare different algorithms that are quite classical, which doesn't involve any machine learning, and also algorithms that does involve machine learning. So as far as we understand some of the flight software, most of them are not involving any machine learning at this point of time. So we did look into comparison of them. Of course, what machine learning technique typically can offer is really this adaptability, this ability that can adapt to some of the, for example, anomalies that you might not envisage from previous flight experience. So on that regard, I think we can really supersede the performance of the classical method. But among the existing machine learning techniques, I think we were also taking part in one of the ESA Grand Challenge. I don't know how many of you know. There was a Grand Challenge back in the 2019. I think we were ranked top 3 worldwide. Of course, the top 3 methods are very similar performance to each other, and we are continuing, implementing new improvement to the machine learning technique. And even within the machine learning technique, there are different families of approaches. So we are comparing those as well. And I did put some of the publication on my slides, which people can Google and pick up and read. Yes, indeed, we did compare them. There are also documented results about them. But this is an ongoing activity. I want to stress, we're not ending it. So this is a continuous, and we are reinforcing our solutions. But also, I have to say, currently it's looking very, very promising. So I think we really hope that with ESA's support, we could set some what I call benchmarks. I mean, a lot of you were talking about in the leadership, internationally. I think ESA, with ESA support, we could be maybe the first to come forward and set benchmarks for machine learning AI-empowered solutions. Because at the moment, I've not seen that, but we can be the first to do that.
Very good. So let's try to pioneer in this field as well. Very good. I think, also all the part of your research about bio-inspired solutions, that is also very interesting. And I was quite interested in seeing this crawling mode of the robots. That was fascinating. One other question I have is actually about autonomous visual GNC and also surface data analytics that you presented during your talk. So, of course, one of the issues, if you wish, of using machine learning is the very limited label data set that we can have available. So I was wondering how you tackle that issue.
So are you talking about existing missions or missions for the future, which we do training and helping to?
Yeah, so I was specifically, I was talking about the autonomous visual GNC, where you displayed the two, so the satellite and the comet, and how to allow the spacecraft to autonomously fly, basically. So I understand that there are indeed labeled data set. Now I also see Michael Bussman. So maybe for the sake of brevity, I would suggest that we can talk about this offline.
Okay. Yeah, happy to. Yeah, very happy. That's a very important question. I think just in short, we have to combine the GNC with verification validation to work together so that we can cope with some of the limitations of the training data set ahead of time to kind of compensate for that shortage. But there are a lot of offline things we can do, but there's also a limitation of what that offline thing we can do in the training.